Okay, everybody, welcome to the MORS Data Science and AI Community of Practice meeting, joined with the Informs Military and Security Society webinar. I think this is an inaugural event, and as someone on the leadership team of both organizations, as well as many other folks on the call today, we're really looking forward to today, as well as future opportunities together to partner and share lessons learned and best practices, applying operations research, analytics, and other emerging disciplines to the field of military and security applications. Just a quick agenda of what we're going to cover today. Well, first and foremost, I'll be our moderator here. My name is Nate Bastian. Been a MORS and Informs member since 2008, so been involved with both societies for a long time. I do want to quickly just highlight the objective of both the community of practice as well as the Military and Security Society, as well as cover a couple items before I kick it over to our really prestigious guest speaker, Dr. David Rios. So for those of you who aren't familiar with MORS, we are a professional society designed and with the mission to really be the premier organization for training and developing military operations research professionals, not just to the military domain, but also to the national security and homeland security community at large. And this particular community of practice is designed to connect both practitioners, researchers, academics, and leaders who are working in the space of data science and artificial intelligence across our large community to share best practices, leverage unique tools, techniques, and technologies. And we hold monthly meetings that take place the last Wednesday of every month at 11:30 a.m. Eastern Time. And if you become a MORS member as well, you'll have access to various materials that we share via our community pages. The Informs Military and Security Society, which we call MASS, the key objective is to really give back to the OR, management science, and analytics communities that are working in the military and national security space. Our primary objective is to foster development, dissemination, and implementation of knowledge, basic and applied research, and scientific technologies that improve the understanding and execution of these types of operations. And we have a variety of forums, both unique to the Military Security Society, as well as Informs at large across the other societies and various venues and events. So if you have any information that you'd like to share at future events, please reach out to us. We're always looking for volunteers to present at the CoP meetings, Informs MASS webinars, etc. And I will share a contact slide here in a minute. But please, at a minimum, reach out to me. I'm involved with both societies. If you have any questions, comments, want to get involved, bottom line is we want you. Couple upcoming events for both societies. Like I mentioned, we do have the monthly COP meeting, and we will be scheduling a future Informs MASS webinar TBD, so we'll post that later. But the next data science and AI meeting is at the end of September. More to follow on the speaker and the topic for that particular session. We also have our 2020 Informs annual meeting, for which we have the Military and Security Society cluster with roughly 10 or so different sessions covering a range of military and security applications that will be held virtually this year. So you can mark your calendar there. And then also on the MORS side, we have our Emerging Techniques Forum, which is our big event that takes place every year in December. And that's will be also virtual this year. And you can see the dates below. So if you have any questions about these events, want to register, want to attend, want to volunteer, get involved, please reach out to me or others on the next slide. This is a pretty busy slide with all the folks involved. Both myself and Mr. Dave Saranchek are the main points of contact for this community of practice. Dave is he's also our president-elect for MORS, and I'm our vice president for professional development. So please reach out to us, whether it's regarding the community of practice or just general MORS questions. And then on the Informs Mass side, you can see our amazing team that we have here, our various officers and council members and at-large members that help put together today, and many of the other amazing opportunities that we have with Mass. So please reach out if you have any questions. But without further ado, I'd like to introduce our main event for today, Dr. David Rios. He's the ACRA ICMAT chair in Adversarial Risk Analysis, which is in Madrid, Spain. He's a member of the Spanish Royal Academy of Sciences. He's the author of 17 books, almost 150 different research papers. His work is in the area of adversarial risk analysis, decision analysis, and Bayesian statistics, and their applications to security and safety. And today, he's going to give us some perspectives on adversarial risk analysis, looking at the intersection of this emerging research field known as adversarial machine learning, and sort of intersecting that with sort of a game-theoretic framework, as well as the decision and risk analysis community. So welcome, David. I'm going to go ahead and make you the presenter. And so give me 1 second here.
Okay, thank you.
Okay, should get the little notification. Okay, I do see slides coming up, which is great.
Can you see the slides now?
Yes. Yep. If it's possible to make it in.
Okay.
Can you make it in presentation mode by any chance?
Sure.
All right. All right. You have the controls. Thank you.
Okay.
Yep.
Okay. So thanks for the invitation for the talk. As Nathan mentioned, I'm going to talk on adversarial machine learning. Here's my email, davidrios@isamat, yes, in case somebody wants to make questions or comments afterwards. So basically the outline will be first to introduce some 2 or 3 slides on machine learning. Then the main topic of interest for this group is when machine learning meets security. So this leads to this relatively new field of called adversarial machine learning. So my idea is to give a sort of quick overview on sort of main topics in this AML. I will explain that most of the research has been framed based on the first paper on this, on adversarial classification, and as such, most of the research is focusing on game-theoretic concepts which are not fully sustainable in a security context, and therefore I shall make an introduce to adversarial risk analysis and how this applies to how can this be applied to adversarial machine learning. Okay, so first, just in machine learning, people use computer programs that learn from experience with respect to a certain task and a performance measure. So the idea is that we try to automate decisions, forecasts, etc., to facilitate complicated tasks. And this has had many successes. I mean, there's a tremendous hype about machine learning based on successes in things like automated translation, automated driving systems, automated speech recognition, and so on. And basically, this has been based in the availability of annotated massive data sets, improved computational power, algorithms and methods, and in certain areas on pre-trained models by express, which can then be translated into other areas, into other application domains. This is one example that we shall be using afterwards to illustrate the issues in security. That's an example of a neural network, a convolutional neural network, a relatively simple convolutional neural network, which is on the right. And we use it, we feed it and use it to try to forecast written digits. That's a sort of very famous MNIST data set. And the task in this with this is to try to forecast whether, well, this person, for example, this first image, whether it's a 9 or it's a 1 or whatever, and then the next one should be a 4, etc., etc. So with a relatively quick exercise, we are able to get accuracies of 99% in forecasting or predicting these digits, which is quite good. So all this machine learning requires lots of testing, and there's various concepts which refer to this area. First of all, we need to ensure that this is doing the correct. I mean, we are implementing it correctly, the algorithms. There's awareness about overfitting, data privacy, etc. But today we're going to focus mostly on the security of these machine learning algorithms and systems, base systems. And there's another issue which is related, which refers to the robustness. Right? So we're going to talk on security and robustness. Okay, so we're going to check how machine learning meets security. The traditional assumption in machine learning is that we are using independent, identically distributed data. This means that we use data generated from same distribution for both the training phase, in which we learn the models, the forecasting, etc., and then the operational phase, in which we use those models to make decisions, etc. So here's we go back to our example. We can actually, I mean, it's conceivable that we train a machine for something, but then there could be some adversaries that are attacking the data, so the data that is receiving during operations is different. And here's one example. So on the first row there is the original MNIST data, and on the second row there is data which has been attacked. So you can see here's pixels from 0 to 256 degrees of darkness. Below, some of the pixels have been attacked with a type of attack which is called FGSM, which we shall mention later on. And we have here we have 10 original images which are forecasted correctly with the algorithm that I mentioned before, with the network that I showed before. But you can see those on the bottom line, they are completely misclassified. For example, the first one, which to our naked eye is, I mean, probably is still like a 0. The algorithm that we use, that we train, and which was correctly predicting before, it now forecasts an 8. The second one, it's a 1, but now it's forecasted as a 7, etc., etc. So that we are able to degrade the performance from 99% to a 62% with a relatively easy attacking mechanism. So you could mention so what, and here's an example which is of interest in one of the projects that we are doing, which refers to autonomous driving systems. So, for example, you can consider a car, an automated car, which requires to perceive from sensors what is the scene, what is going on, other persons, other cars, and so on. What is the road? Are there any obstacles? So you can see an image that the cameras of the car are perceiving, and the kind of segmentation that the algorithms inside the car would be doing. So it would recognize that there are some persons, and consequently it would brake. Below there is the same perturbed image. So there's some, I mean, you cannot appreciate it from there, but there's some slight modifications of the pixels. And what happens is that these slight modifications make the persons disappear as implemented in the recognition algorithm. So where the car should recognize persons, in this case recognizes nobody, no obstacles, and where it should brake, it accelerates, and you can imagine that one of these cars becomes a weapon, right? So that's the kind of problems that we could face. So the idea is that we develop these algorithms, automated systems, machines to perform some task. But in some contexts, there's bad guys, bad persons. There's attackers, adversaries who are intelligent and try to learn how we are predicting and making decisions, and as a consequence they might change data, or they might try to change the structure of the problem to fool us and make us make incorrect decisions with potentially bad consequences for us and good consequences for them. As an example, here's an exercise that we perform on spam detection. So we use a classical test, a classical data set to try to verify how good were a few statistical or a few classification algorithms. So what we perform classification with those algorithms, and then we attack those spam data. So we try to make them, we attack in a certain way to try to fool those algorithms. So you can see here on the left column that these 4 algorithms: an naive-Bayes, a logistic regression, a neural network, a simple neural network with 2 layers, and a random forest. They perform reasonably well with in detecting spam. So there's an accuracy of 89% or 92%, 94%, etc. But then when we attack the data, there's a tremendous performance degradation. So for example, for naive-Bayes, it goes from 89% to 77%. So our simple attacks allows us to fool the algorithms that we are using with a benefit, with a potential benefit for the attacker, and a potential loss for the defender.
Hey, David, real quick, sorry to interrupt. Can you hide the little thing at the bottom there? Yeah, thank you. Appreciate it.
Okay, sorry. Thank you. Sorry. So so there's more and more systems that are being deployed, and they could be subject of attacks. So examples refer to content filters, which are very important for, I don't know, from fake news detection to spam detection that you mentioned, fraud detection, etc., that kind of things. There's military systems, there's predictive policing systems, autonomous driving systems, and well, all these systems that are start to be deployed are the subjects could be attacked, and some of them have already been attacked, and that's a problem. By the way, there's a very good, from a policy perspective, there is a very good report by Committer on this area, which I I have cited here. So we have these machine learning systems, these security issues, and this leads to the field of adversarial machine learning. And in the next 10 minutes or so, I will explain the key ideas, key concepts, in case somebody is not familiar with this area. So the tour is basically can be summarized in this slide. So there's the pioneer paper by Delivi et al. On adversarial classification, and this has been extremely influential in this research area and application area. So there's a lot of history, and then there is a few review books, recent review books, review papers, and a couple of policy interesting. One is the committer paper that I mentioned, or report, and then there is I believe NIST is at the moment. I don't know if it has finished already, but it was during spring. It was trying to standardize the language in this area. So this means that it's a quite important. And as a bottom line summary of all this research is that Delivi et al. Has been extremely influential, and it has framed most of the research within the game theoretic arena. And this entails from my point of view, and that will motivate the kind of research that we try to do. This entails a few common knowledge assumptions that in the security arena, it's probably hard to accept, and that would require probably new attempts, as I shall try to propose. Besides this, there's these kind of issues are also interesting in other related or sister areas, which are things like adversarial signal processing, security games, and so on. These kind of ideas are also discussed in these other related or very close areas. So let me go a little bit on a couple of slides on what is adversarial classification. There's a classifier, the system which is being deployed to classify automatically, and there's an adversary and there's to simplify the discussion, suppose there's two classes. So there's malicious and instances and innocent instances. There's a spam and non-spam, fraud and non-fraud, and whatever the application is. For a moment, assume that both. For most of the talk, assume that both agents try to maximize something. So this something that we try to maximize will be expected utility for our discussion, and there's common knowledge as conditions that we shall be discussing. In this case, to start the discussion, assume that both agents know the expected utility of the other agent, and this is known. And even in this kind of context, finding nice equilibria is extremely complex. And here's what this sort of initial paper by Delivi et al. Does is basically they propose a scheme in which basically the classifier operates with untainted data, with clean data. So the classifier feeds her algorithm, her model with untainted data. The adversary who knows this, given an instance, chooses what is the optimal attack against that classifier. So the adversary knows that optimal classifier, original optimal classifier, and then the classifier who knows this optimal attack will try to defend her classifier against such optimal attack, and so on. Okay. So this is like a forward myopic approach. Okay, and then there is a very strong common knowledge in the sense that the classifier knows a lot knows all the parameters of the attacker, of the adversary, and the attacker vice versa knows all the parameters of the defender, of the classifier. So it's interesting to, if you read this paper, that the authors, Delivi and his colleagues, acknowledge this limitation. So they say, well, one of the problems that we should work on is trying to improve on this or relaxing these conditions. But it's also interesting to see that most of the research hasn't departed from this path. Another important set of problems is what is called adversarial prediction. That's the distinction that is made in machine learning between classification and prediction. In classification, you predict discrete labels. In prediction, you predict continuous labels. So it's you can see it's also as a continuous regression, right? So it's the same kind of problem, the same kind of context. The only difference is that the labels are continuous. And here there is the work by Bruckner and his colleagues. And again, they use Stackelberg prediction games for sequential when there are sequential decisions. So first the learner chooses, and then the attacker transforms the data, or NAS prediction, in which there is simultaneous decisions of both agents, of both players in this adversarial prediction game. But the common knowledge, these very strong common knowledge conditions are preserved. Another concept which is very important and has made it to the media many times, and it's in part the interest of this in this adversarial machine learning community, and it's especially quite important for the deep learning researchers, are what is called adversarial examples. And it's actually the kind of example that I showed you before with the car. So basically, you get a correct classifier which works pretty well with images. Then you add some attack pattern, which is, I mean, there's no pattern. I mean, you see, you appreciate no pattern with your eye. The corresponding image is quite similar to the human eye, but the classifier is completely fooled, and it provides incorrect classifications, and this has the consequences that. So these are examples based on types of attacks, various types of attacks which have been devised. In particular, this is called the fast gradient sign method, and the kind of transformation. The kind of transformation used is on the bottom of the slide, and this requires, if you think for a minute, this requires that knowing the loss function. So this requires that the attacker knows the loss function. Afterwards there's some other, but originally this requires, I mean, that the attacker knows a lot about the defender or the classifier. Another concept which is very important is adversarial training, which is, well, you have these attacks. How can we train our machines to be robust against these kind of attacks? And basically, it's training models with attack samples. Well, it's from a formal point of view, this is the kind of problems that are solved, which have a game theoretic interpretation. There's been also, as before, there's been a few variants on adversarial training, etc. But these are important sort of seminal ideas. So having this, basically, there's three core topics in adversarial machine learning. The first one is modeling threats, depending on what are the attacker goals. There's an emphasis on what is called integrity, availability, and privacy violations. That's typical from cybersecurity, but there's, I mean, you should consider other things like killing, I mean, the number of people killed or injured, environmental impact. So there's other objectives that could be considered. Depending also on what is the attacker knowledge, the attacker could know
about what is the training data or the features that are being used by the algorithms. What is the actual algorithm being used? What are the weights? I mean, depending on how much the bad guy knows. We talk about white box attacks when there's perfect knowledge. That's a sort of as in Delivi. And then there is intermediate attempts like gray box attacks or black box attacks. And also, depending on the capabilities, people talk. Sorry?
I think someone wasn't muted. Thank you.
Sorry. So also depending on the capabilities, people talk about poisoning attacks depending on training, or when the attacks is during training, or evasion attacks when there is during operation. The second topic is about simulating attacks. Typically people study how the attacks, how I'm going to be attacked using some kind of optimization problem depending on the previous features that I mentioned on goals, knowledge, and capabilities and strengths. And the third kind of main topic refers to security measures. How do you defend? And typically you defend through reactive defenses. So one main topic is detecting attacks. That's very important. Another possible approach refers to retraining frequently. Okay, so but that could be very time consuming. And the other kind of defenses refer more to more proactive. So you try to make robust machines, robust algorithms, which take into account somehow the potential, or try to forecast how the adversarial manipulations are going to be. People also use randomization, information hiding, etc. Many of the things coming from the let's say physical security world. It's the same kind of things. I put this as a sort of anecdote to, first show that there's a lot of interest on this. So there's the NIPS competition on adversarial machine learning organized by Google first, with lots of participants. But the second one is that it's a very difficult and very competitive arena. So there was a winner who claimed that he was very good against 95% of the attacks at that competition. But just a few months later, somebody defeated all these algorithms. So this talks about a sort of new arms race. An arms race with cycles in which people defend, then people discover attacks, and then people discover defenses, etc., etc., etc. And you can imagine that there's competitions between artificial intelligence or operations research experts in various countries fighting other countries, etc., etc., etc. We should say also that there is one important development in this is the Clever Hands library, which has lots of examples, algorithms, etc., which facilitate reproducibility in this area. And that's the sort of 10-minute summary. Actually, everything is now adversarial in machine. So you can, whatever you think of. So if your favorite is our support vector machines, there's people working on adversarial support vector machines. If you're interested in ARIMA models, then attacks to ARIMA models and so on. It's mostly done from a game theoretic perspective with common knowledge too commonly assumed. There's not so much acknowledgement of the uncertainty that is available about attackers, which is what happens in security, as you probably know. And it's a very difficult area, and it's very relevant from an applied point of view, both from national security and cybersecurity perspectives. So this is the stage, a brief introduction to what we try to do. That's part of my that's my work for ACRA, for the ACRA chair. What we try to do is adversarial risk analysis. For those, so let me go like 5 minutes to explain it. So basically, it's moving from risk analysis to adversarial risk analysis. So we, my team, my group have done a lot of work on aviation safety and performing risk analysis to try to avoid or mitigate the destruction of airplanes or killing people, etc. For that, we introduce people introduced slides, but this introduces, I mean, this kind of risk analysis, which is a standard. But risk, there is, I mean, in aviation safety, you can use airplanes to for terrorist attacks, and that's initiates in part this approach to adversarial risk analysis. So in this, in artificial intelligence, there's actually the same kind of differentiation between what is called safe artificial intelligence versus secure artificial intelligence, which is the kind of topic that we do. So very quick, the ideas with a simple game. It's a simultaneous defend attack game. So there is a defender which deploying defenses, an attacker which simultaneously submits attack. There's a result of the interaction of the defender and the attacker. The defender gets some utility and the attacker gets some results also, some utility. So under very strong common knowledge assumptions, each agent knows the beliefs and utilities or the expected utility of the other agent, and therefore we can compute Nash equilibria, right? But that's very strong, at least in many security settings. I mean, you have spies, informants, you observe the actions, etc. But I mean, this is not sufficient to have all the information, as you probably know. So sometimes, well, many times, at least in security, some information is not common knowledge, and typically this is introduced as a game of incomplete information in which there is a type of, I mean, the defender and the attacker has what is called types, which are features which are known by him or her, but known by the other, but not known by the other, and which affects the utilities, the utility of the defender and her beliefs, and the utility of the attacker and his beliefs, right? So this should be a tau A. Sorry, by the way, there's a mistake. And the thing is that there is a common prior over the types. Okay, so that's this is what it's done in incomplete information games with base Nash equilibria, but there's still this common prior which has been criticized as well. So basically, once based on the types, there is the concepts are strategy functions. Then we compute the expected utilities given the types for both the defender and the attacker. And then we have the concept of base Nash equilibrium, which is traditional due to Harsanyi. But as I said, this is under the common prior assumption. Okay, how we can proceed alternatively is viewing this problem as one of decision analysis. So from the defender perspective, the problem is based on the by agent influence diagram, it is viewed like this right now. So now the attacker is an uncertainty for me as a defender. So so I just try to solve this problem, this standard decision analysis problem, which is, I mean, it's quite a standard. The only thing which is exotic is that I need to forecast how the defender is going to attack me. So the rest are standard elements in. So I need to assess some utilities of the results of the attack. So I have my military engineers giving me this information, I make a forecast of the results given the defense. That's also kind of easy, but this has a strategic element, the how to forecast. I could try to forecast this with standard expert judgment techniques. I mean, in the end, it's another uncertainty, but we have seen that you get better forecasts, better quality forecasts if you make the kind of the compositions that we try to undertake in what we call adversarial risk analysis, which is just trying to think of what would be the problem, what would be the problem of the attacker, what would be the problem of the attacker. We formulate the decision problem that the attacker would solve, but then we recognize that we have no access to his utilities and his probabilities. So what we do is model our uncertainty about his utility. So we have a random utility and our uncertainty about his probability. So we have random probabilities, and then we solve. I mean, rather than finding the optimal action of the attacker, what we find is a distribution over his optimal. What would be his optimal attacks? Okay, in this, some of this information is kind of natural to think of, but this capital pi that I'm marking now is kind of complicated because I need to think of how the attacker is thinking about me. And the moment I think of this, we get these kind of recursions. So what we do is we try to model this recursion until a limit in which we have no knowledge or little knowledge. And in that case, we put a non-informative prior, and then we solve backwards the problem. So this is close to what is called in game theory level K thinking. So I just explained this with this simultaneous defense template, but other templates which are usual in security decisions, like the sequential defend attack, sequential attack defend, or sequential defend attack defend, or sequential defend attack with partial or with private information, can be dealt with simultaneously. And we call these templates because the real problems that then we try to solve require expanding these templates with additional uncertainty nodes. For example, here, this is how we expanded for a sort of cybersecurity problem in which we have not only attacks, targeted attacks, but we have non-targeted cyber threats, etc. So we have insurable and uninsurable impacts, etc. I mean, we can expand this, and also in many applications we need to expand to cases in which interactions are richer between agents. So there's times in which our decisions are sequential, but in others are simultaneous, and then this could be repeated over time, etc., etc., etc. So the idea is how do we, and basically the kind of algorithms that we use is basically we decompose the problem in sequences of simultaneous and sequential problems, and with some kind of algorithmic tricks, we can handle these more general interactions. For this, for MAS and MORS, we have done a few examples referring to counterterrorism, cybersecurity, national defense, and urban security. And if you want further details, just email me. But we have done things like in airport protection, railway system protection, cybersecurity protection, piracy, fighting against UAVs, underground protection, etc., etc. With various. Here's a little classification depending on who was the defender, who were the attacker or the attackers, what were the specificities. There was a single site, multiple sites, cascading effects, etc., 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 and the kind of template from which we started. Okay, but now, yeah, sorry, and as final discussion, ARA and game theory provide different solutions because they are based on different information and different assumptions. So we have examples, many examples. The four sort of related concepts in game theory. So ARA solutions respect dominance. ARA solutions respect a kind of iterative dominance concept. There are some relations with fictitious play and with level K thinking. There's also some relations with Bayes-Nash equilibria. And the kind of approach that now we try to follow is we try with the game theory solution. We then perform a sensitivity analysis, and if the solutions are sensitive, then we try the adversarial risk analysis solution, which tends to be more robust. And as a final comment, most of the discussion that I mentioned was on adversaries that maximize expected utility, but you could think of an extent to adversaries with different rationalities. For example, they could maximize a prospect theory functional or something like that. Okay, so just some quick ideas on how this paradigm or this different approach to conflict can affect or can be used in adversarial machine learning, which is our core focus right now for research. I can just reproduce the pioneer paper on adversarial classification by Delivi and his colleagues through adversarial risk analysis. So basically, the kind of graphs that we use is on the left you have the standard classification. So a classifier receives instances data X, which is related with the type of either malicious or innocent entry, and he needs to make sorry, a classification. See, he has to decide whether this is malicious or innocent, and depending on the type and his decision, he is going to take a utility. Now, in this adversarial classification, there's another actor who can transform the data. He can fiddle the data, so he can attack through A, and we will not see sorry, we will not see the actual data X, but the perturbed data X prime, right? So the classifier in this context will observe this perturbed data, and based on that, he has to make his decision, right? And depending on that, he will get some results, and depending also on whether the attacker is capable of fooling the classifier, he will get some utility. So we use, as before, what would be the defender or the classifier problem, which is on the left, and to assess an adversary aware classifier will have this uncertainty. She doesn't know how she is going to be attacked, how the data is going to attack. So for the uncertainty, this uncertainty, to facilitate thinking about this uncertainty, we try to consider what is the problem that the attacker is going to do. We simulate from this problem, and then with this, we try to find the sort of random optimal attack, and that's the distribution that we're going to use. And then we have a sort of standard Bayesian decision analysis problem, right? So we have algorithms. I'm not going to go into detail. You need to distinguish between whether you are using a generative or a discriminative classifier. We have a few algorithms. I'm just it's more interesting to see that that these things work. So I'm putting back the example from before on spam. You remember that we had a pretty good performance in the beginning, right? When we were dealing with tainted data, the performance degraded a lot, so we were in a bad position with using our standard classifiers with attack data. But now with these kind of algorithms, we take into account the possibility that you might have been attacked. The performance improves, so it's much better. So somebody using an AI-based adversary-aware algorithm performs much better than somebody who is not aware, and does not take into account that she could have been attacked by a bad attacker, right? So basically, the message is that I mean, it's very computational intensive, but we can translate these ideas to this adversarial machine learning to get some benefit. We benefit because we don't use so strong assumptions. We get more realistic models, and we get reasonably good solutions. We have extended these kind of things to reinforcement learning, for example. So that's another type of problem in machine learning. Basically, for those of you who remember sequential decision making, so it's a way to deal with, it's an algorithm for solving Markov decision processes based on, I mean, the core idea is Q learning. So in this kind of context, in which there's a space of states, there's a space of actions for the agent that we support. There's a transition and there is a reward function. There could be attackers. So somebody could be trying to attack you in your sequential problem. So we augment. So we consider what is called threatened Markov decision processes. So we augment the problem with the attacks. And we need to make a forecast of what the attacker is going to do. Based on that, we can extend Q learning. And the idea, the core idea, again, as before, is trying to get good forecasts of how the attacker is going to attack us. And well, there's 2 or 3 principles that we have considered, but there's room for much better ideas for sure. So another thing that we are trying to do is, I'm gonna summarize because time is running. Rather than going to various like classification, prediction, reinforcement learning, etc., through various machine learning or statistical problems, we are trying to get a sort of general approach. We call it adversarial statistical decision theory. So it is basically we try to think of based on the standard statistical decision theory approach, theory, methodology, concepts, etc., how an attacker could attack. So he could fiddle with the data, or he could be a structural attacker, or he could be a simultaneous, and he could perform simultaneous decisions, right? So based on that, we are trying to build a general theory which supports all these kind of things. Okay, I'm gonna skip this. Finally, for discussion, basically what we do is we try to do statistical or machine learning or risk analysis perturbed by adversaries. Traditionally, they're treated from a game theory perspective, which entails common knowledge, and this is debatable, to say the least, at least in the security arena. We try to use this adversarial risk analysis approach to try to mitigate this common knowledge. we have different opponent models beyond expected utility, and we can combine also various rationalities through mixtures. So there's many problems, like as I mentioned, trying to get a generic approach that allows to then deal to point estimation, interval estimation, hypothesis testing, etc. Reinforcement learning is very important in many applications. So how reinforcement learning is being attacked. This is a very, I mean, one of the bottlenecks is the computational, I mean, less assumptions entail very or much stronger computations. So we need to be more efficient. And there's many interesting problems that practical problems like fake news detection, malware detection, phishing, autonomous driving, and more relaxing, but it's still relevant for security, like poker or dominoes or playing dominoes. A few references, and finally, again, thank you. In the first slide, you could see that this is probably, I mean, this is the work with I don't know, there were like 15 or 20 people who have I mean, with whom I have collaborated in this, and if you are interested in these kind of topics, I mean, I'm also very interested, so I would be very happy if any collaborations come across after this talk. Thank you.
Great. Thank you so much, David, for the talk. I know many of us in this call have a lot of interest in this space as well from a research perspective. And on the DoD side, we actually have the DoD IC, which is Intelligence Community Adversarial AI Working Group. So I might try to get you to come be a guest speaker there. On the Army side, we have a robustness and resiliency working group from our Army AI safety working group. So there's a lot of opportunities. So yeah, to collaborate. So I can follow up with you offline. We do have time. We do have time for maybe 2 questions because we are kind of at the end here. I'll read them out. We got one actually from Dave Saranchek. He says, can you comment on how long it takes to train models using your algorithm as compared to normal training?
Okay, so I can comment in general. For example, for this spam classification or this fraud detection kind of problems that we have done, I mean, the training is more or less the same. You must think of there's one distinction that I didn't mention is at least these problems that I mentioned are on the adversarial classification that I mentioned or I discussed was on operation time. So there is another approach which is on during training time. So this adversarial training, we can make it more robust with this. And in this case, the training time would be comparable to a standard. The sort of computational bottleneck comes when you try to do this on real time, right? Because I mean, this is quite important because the bad guys are quite clever and they try different things, they try different data until they fool you, right? So you need to take into account this during operations. So I mean, for the kind of problems that we send, we use. I mean, roughly it's about 10 seconds. I mean, you have to think of what are the potential attacks and then assess the distribution. And we took about, they take us out in the kind of problems that we use, it's about 10 seconds, which for some applications are okay, but for other applications are not competitive. So one of the bottlenecks is computations during operation, during real-time operations. Yeah, but this is a very important problem.
Great, thank you. And I guess I'll just one last question. One of the comments was, basically thanking you for saying that it's good that you've looked at other measures, these objective functions other than expected utility. And he asked, could you say a few words about that? It looks like some of the like minimax risk and things like that. Any comments on that?
Yeah, sure. So our philosophy, our way of thinking is, well, I'm supporting the defenders, the good guys, the Spanish army or the Spanish police or whatever, Madrid police, whatever. So I have this is my client. Okay, so let's talk like this. So I have them in contact, so I can convince them to try to adopt a decision analysis expected utility model. But I don't have the bad guys to interview them. I mean, they could have spies or informants, whatever, right? But I don't have them. So, but what I can think of is that they try to do as best as they can, given their constraints and resources, right? As you can read from terrorism manuals, etc. So what the most general model that we use for them is a prospect model. So we assume that they maximize prospect, a prospect functional. And then, since we don't have them to get the values and the weighting functions in their prospect models, we put uncertainty on them, and then the mechanics would be the same. But since we cannot ask them directly, that we use the sort of more general functional for them. But you could put we have done this with various rationalities. We have put minimax adversaries. We have put level 2 thinking adversaries. We have put Bayes-Nash equilibrium adversaries, and we have put combinations of these kinds of adversaries. This is close to also what is called cognitive hierarchies in game theory. So this is a concept which is close to that approach.
Great. Thank you very much, David. And again, your great talk, and looking forward to seeing how this field just continues to grow and evolve. And there's a lot to do. So it's a great area to work in. So thank you. And I guess everyone else on the line, thank you for attending today. Again, if you have any questions about MORS or Informs Military and Security Society or Informs at large, just please feel free to reach out. And again, thank you, and have a good rest of the day and rest of the week. Take care.
Thank you.